Welcome to the video on solving equations and inequalities using graphic methods. Suppose we were given some function without an algebraic formula, just graphically, and suppose that function were called f. We might be asked to solve something like this equation, f of x equals 0. Well, to solve an equation means to find an x value or multiple x values for which that equation is true. The way we can interpret the equation f of x equals 0 is that we need to find all x values for which the y-coordinate of the function equals 0. If I'm going to find all the x values that make this equation true, I'm going to find all the points that have a y-coordinate equal to 0. Well, here are the 3 points on this function that have a y-coordinate of 0. But remember, I'm solving for x in this equation. So I want to find all the x values that correspond to these points whose y-coordinate is 0. And you can see just by looking at the graph that those x coordinates are -3, -1, and +3. So I'm going to express my answer this way. Something worth noting here, this is not interval notation. You'll notice the braces around the answer. And the commas in here don't mean through like they would in interval notation. So we're simply saying there's 3 numbers that make this equation true, and here they are. Suppose we were asked to solve an inequality. F of x is less than 0. Well, we're looking for all x values that make this inequality a true statement. So for f of x to be less than 0 for some particular x, it would have to have a y-coordinate less than 0. So I now want to find all x values for which the y-coordinate of this function is less than 0. If I want to find all the x values that make that true, I'm going to first find all the points that make it true physically on the graph. So now I'm trying to find all the points that have a y-coordinate that is less than 0. If you interpret less than 0 as being negative, which it is, then we can see that all these points in red have a y-coordinate less than 0. And when I say all these points, I don't mean the round red dots. Those are not points whose y-coordinate is less than 0. You'll notice I've used an open circle there. That's my notation, and all mathematicians' notation for this point doesn't count or isn't included. Well, the points on the x-axis have a y-coordinate that's exactly 0. When I say all the points in red, I mean literally all infinitely many points anywhere on this function that's below the x-axis. But remember, I'm solving the inequality, meaning I'm finding x values that make that inequality true. So I now want to find all the x values that correspond to these infinitely many points in red. And again, I'm not including the 3 open circles. Okay, well, here's where it gets a little tricky. Here's the solution expressed in interval notation. Now, there's no mathematical way, there's no step-by-step algebra procedure to get this. This answer simply comes from a realization that there are 2 sections on this curve that are below the x-axis or that have negative y-coordinates. And one of them, on the left, contains all x values from -4 through -3. And the other contains all x values from -3 through 1. Sorry, -1 through 3. And notice that I have included, by putting a bracket on the -4, because this statement is actually true, when x is negative 4. But I've put parentheses in my interval notation by the negative 3, the negative 1, and the 3, because this is not a true statement when x is those three values. So those are the symbols of exclusion in interval notation. Why is this not a true statement when x is negative 3, negative 1, or 3? Because for any of those, f of x actually equals 0 and isn't less than 0, as indicated in the inequality. Suppose we were asked to solve this inequality. Again, solving means to find the x value or x values that make it true. So what x values make f of x greater than or equal to 0 true? Well, one way to interpret that is I need to find all the x values for which the y coordinate of the function is greater than or equal to 0. To do that, I should find all the points that have a y coordinate greater than or equal to 0. And when I say find the points, I mean find them physically on the graph or identify them. Well, you can see that all these points in red, including the ones on the x-axis, notice the solid dots. All these points in red, all infinitely many of them, have the property that their y coordinate is greater than or equal to 0. But remember, I'm solving this equation for x, so I want to find all the x values that correspond to these points. And here's again where it gets tricky. There's no algebraic way to do this, but here's the solution. And where does this come from? Well, it comes from a realization. The realization that if x is any value that corresponds to anything here in red, then the function value of x, or the y coordinate associated with that x, is going to be greater than or equal to 0. And so the first interval on the left goes from negative 3 through negative 1. Notice the brackets in the answer to represent the inclusion of the endpoints. This is a true statement when x is negative 3, and it's a true statement when x is negative 1. Why is that? Because f of negative 3 and f of negative 1 are both equal to 0. Hence, the greater than or equal to 0 is satisfied. Likewise, for the second interval in the answer, 3 through infinity, the 3 is included. Again, because the original problem is true when x is 3, f of 3 is 0, and therefore 0 greater than or equal to 0 is a true statement. Let's look at a different function. Suppose we had some function and it was called k for no particular reason. And suppose we were being asked to solve k of x equals 2. Well, to solve means to find all x values that make this a true statement. That's what solving means. So I want to find all x values for which k of x equals 2. In other words, for which the y coordinate of the function equals 2. And you can find them visually. But to do that, I need to find all the points that have a y coordinate of 2. Well, there's only 2 points on this graph that have a y coordinate of 2, and there they are. But remember, I'm solving for x. And so I want to find the x values that correspond to these 2 points in red. Well, the x values that correspond to them are negative 1 or 5. Notice this is not interval notation and does not represent negative 1 through 5 or all numbers between them. The comma, in other words, does not represent through as it would in interval notation. You'll notice I have braces around the end of the answer, and that simply means that it's a set of numbers, negative 1, 5, and not negative 1 through 5 as interval notation would indicate. Suppose we wanted to solve k of x is greater than 2. Again, I'm solving for x, that means I want x values that make this a true statement. But k of x for a particular x value is the y coordinate associated with that x value. And therefore I want to find all x values for which the y coordinate of this function is greater than 2. But to find all the x values, I should first find all the points that have y coordinates greater than 2. And we can find this visually by looking at the area in red here. First of all, notice the open circles. Those are the symbols of exclusion, meaning those 2 points in red open circles do not satisfy this equation. But all the other points in red on the semicircular arc do satisfy the equation. Why do the 2 points with the open red circles not satisfy the equation? Because at those 2 points, the y coordinate is 2, not greater than 2. So once you have the realization that all the points in red, excluding the open circles of course, have y coordinates greater than 2, you can ask yourself, what are all the x values corresponding to these points in red? And they're everything -1 through 5. You can see that simply by looking at the graph. Now notice this is interval notation because of the parentheses. And so what I'm saying here is all x values -1 through 5, but excluding -1 and 5 themselves, will make this statement true. Here's another inequality to be solved using k. Again, I'm solving for x, meaning I'm looking for all the x values that make this a true statement. And so I want to find all the x values that have a y coordinate less than or equal to 2. Well, if you look at the graph, you'll notice to find all the points y that have y coordinates less than or equal to 2, they're all here, including the solid dots at -1 and 5 themselves. Why am I putting solid dots here? Because I'm including those points because they have y coordinates that are actually equal to 2, and hence the less than or equal to 2 part is satisfied. So I've identified all the portions of the graph that have y coordinates less than 2, but again, I'm solving for x here. So I need to find the x values that correspond to all the points in red here. Well, again, it gets tricky because there's no algebraic way to arrive at the answer other than to look at the picture and then come up with the answer. But it's worth explaining that I have the union symbol here to join 2 separate intervals on the x-axis. The first interval, corresponding to the left side of the picture in red, represents that all x values -infinity through -1, including -1 itself, notice the bracket of inclusion, all of those x values satisfy the equation. And all x values, notice the right half of the graph in red, all x values from 5 through 6, including 5 and 6, also satisfy the equation. Sometimes we have to solve inequalities that involve 2 functions. But suppose we were trying to solve the inequality h of x is greater than or equal to g of x. Again, I'm solving for x here, so I need x values that make this statement true. Well, one way to interpret this statement is this. I'll pause while you read it to yourself. So if we're looking for a particular number x that makes this true, or numbers, then we're looking for a number or numbers for x for which h of x is greater than or equal to g of x. Well, h of x is the y coordinate associated with the value of x on the function h, and likewise for g. And so essentially we're looking for where on this graph does the h have a bigger y-coordinate or equal to y-coordinate than the g. But for h to have a bigger y-coordinate or equal to y-coordinate than g, we'd have to be somewhere in this red region in the middle. Because there, for every single point there, and I don't just mean the two solid round red dots, for all infinitely many points shown in red, the value of h is greater than the value of g for that particular x value. Another way to see this is these are all the points for which the function h is higher than the function g, or equal to. And once you've determined visually by just looking at the graph that these are all the points for which h is greater than g, you can simply answer by giving the x-coordinates of all those points. So what are the x-coordinates of all the points in red? Well, they're all values from -2 through 1. Notice the use of interval notation, and notice the comma representing the concept of through. Notice also I've put brackets to include the endpoints. And why is that? Well, because this inequality, h is greater than g, greater than or equal to g, is true at those endpoints, because at those endpoints, h and g are equal to each other. If h and g are equal to each other, then h greater than or equal to g is a true statement. And lastly, let's look at g greater than h. To solve the inequality, we need to find all x values for which the g function is greater than the h function. Well, that's the same as saying the y-coordinate of g is greater than the y-coordinate of h. And we find this visually by looking at the graph. Where on the graph is the g function bigger than the h function? Well, it turns out for all these points here, you can see just by looking that anywhere in this either of these two red regions, g is greater than h. Notice I've excluded -2 and +1 by using open circles there, because at -2 and at 1, g isn't greater than h, it's equal to h. But anywhere any of the points in the red zones has a y-coordinate for g that's greater than the y-coordinate of h. Another way to think of that is g is above h in those two regions. Remember, I'm solving for x. So now that I've identified in red all the points where g is greater than h, I need to list the x-coordinates of those points. Here's how I've listed them. Using interval notation to represent the two separate intervals, the first being -∞ through -2 on the x-axis, and the second being +1 through infinity. And notice the parentheses of exclusion, specifically at 1 and -2, because at those two values, g isn't greater than h, it's equal to h. And that concludes this lesson.